and welcome to a new video. In this video, I'll make a brief introduction to line integrals and its related theorems. This video is going to be quite theoretical, so I do not recommend it if you're not fully healthy, so promise me you're fully aseptic. So as you can see, I've drawn this picture in advance, so don't blame me for that. And as well, I call this curve K. That's because the word for curve in my language is kurva, but do not misinterpret it. It's not Russian or something like that. So, what is a line integral really? Let K be a curve in the xy plane which connects point A of A1 and B1 here, and B of A2 and B2 here. Let then P of X and Y and Q of X and Y be single valued functions defined at all points of K. Then subdivide K into n parts by choosing n-1 points on it given by xy and y1, x2 and y2, and so on and so forth until xn-1 and yn-1. Then call delta xk equal to xk minus, oh, I'm terribly sorry, minus xk minus 1, and delta yk equal to yk minus yk minus 1, where k is given by an integer from 1 to the specific value n. Where A1, B1 by definition is equal to x0, y0, and A2, B2 by definition is equal to xn, yn. Then, by this diagram, suppose that the point alpha k, eta k are chosen so that they are situated on k between points xk minus 1 and yk minus 1 and xk and yk. Then, after that, form the sum running from k equals 1 to n of p of alpha k eta k times delta xk plus q of alpha k eta k times delta yk. The limit of this sum as n goes to infinity in such a way that all the quantities delta xk and delta yk approach 0, if such limit exists, is called a line integral along k, and this is denoted by the integral over k of p of x and y dx plus q of x and y dy, or integral from a1 b1 to a2 b2 of p dx plus q dy. So how do we know if the limit exists? Well, the limit exists if p and q are continuous, or piecewise continuous at all points of k. The value of the integral depends in general on p and q, the particular curve k, and on the limits a1, b1 and a2, b2. In an exactly analogous manner, one may define a line integral along a curve k in three-dimensional space as... now I'll make an abnegation, because I don't like writing lim as n goes to infinity, so I'll just write as n goes to infinity of the sum running from k equals to 1 to n of capital A1 of alpha k, eta k, sigma k times delta xk plus capital A2 of alpha k, eta k, sigma k times delta yk plus capital A3 of alpha k, eta k, sigma k times delta zk. This is equal to the integral of a k of capital A1 dx plus capital A2 dy plus capital A3 dz, where capital A1, capital A2 and capital A3 are functions of x, y and z. Other types of line integrals, depending on particular curves, can be defined. For example, if delta sk denotes the arc length along curve k, say, between points xk, yk and xk plus 1, yk plus 1, then the limit as n goes to infinity of the sum running from k equals to 1 to n of u of alpha k, eta k times delta sk is then equal to the integral over k of u of x and y. Yes, this is called the line integral of u of x of y along curve k. Extensions to 3 or even higher dimensions are possible. Now when the concept is introduced, I'll go into more details. So now I'll go into the vector notation for line integrals. So it is often more convenient to express a line integral in vector form as an aid in physical or geometric understanding, as well as for brevity of notation. For example, we can express the line integral in the form the integral over k of capital A1 dx plus
capital A2 dy plus capital A3 dz
as the integral over k of A1 in the I direction
plus capital A2 in the j direction plus capital A3 in the k direction,
dotted with dx in the I direction
plus dy in the j direction plus dz in the k direction.
And this simplifies to the integral over k of a where A
capital A1 in the I direction, plus capital A2 in the J direction, plus capital A3 in the K direction, and dr is equal to the x in the I direction, plus the y in the J direction, plus the z in the K direction.
The line integral is a special case of this with z equal to 0. If at each point x, y, and z we associate a force F acting on an object, that is, a force field is defined, then this can be expressed as the integral over k of F dotted with dr. This represents physically the total work done in moving the object along the curve k. Now to the evaluation of the line integral. If the equation of a curve k in the plane z equal to 0 is given as y equals to f of x, the line integral is evaluated by placing y equal to f of x and dy equal to f prime of x dx in the integrand to obtain the definite integral. The integral from a1 to a2 of p of x and f of x dx plus q of x and f of x times f prime of x dx. I should really put curly brackets here, but never mind. This is then evaluated in the usual manner. Similarly, if k is given as x equals to g of y, then dx equals g prime of y dy, and the line integral becomes the integral from b1 to b2 of p curly brackets g of y times g prime of y dy plus q of g of y and y dy. Then if k is given in parametric form as k equals to phi of t or something like that, and y equals to psi of t, the line integral becomes the integral from t1 to t2 of p of phi of t psi of t times phi prime of t dt plus q of phi of t psi of t times psi prime of t dt. It's becoming tight out here. Where t1 and t2 denote the values of t corresponding to points a and b respectively. Combinations of the above method may be used in the evaluation. Similar methods are used for evaluating line integrals along space curves. So the same method holds in multiple dimensions.